Welcome to Ask and Learn.
Okay, so once again, we have a problem with us. This is we're given the Fitzhugh-Nagumo model, and it happens to be a differential equation with the following expression: dv over dt equals to negative v squared minus 1 plus a in parentheses v plus a and then square bracket. So this is a differential equation, which means that it has variables together with their derivatives. It's possible to have first order differential equations or second order differential equations, for example. In our case, we have a first order differential equation because this is just the first derivative. And it's an electrical impulse in the absence of some kind of relaxation effect, and it obeys this type of differential equation. So another thing we're given is the fact that the constant a lies between 0 and 1. So that's a fraction. Anything between 0 and 1 is a fraction or decimal. In part A, we're supposed to assume that dv over dt is 0. And this simply means that Vt is not changing. Okay, Vt is not changing. So this one would assume that Vt is a constant. It's a constant variable. Remember that Vt just stands for the electrical impulse. Electrical impulse of a neuron. Electrical impulse of a neuron. So in part A, I'm just going to shift to the next page. In part A, they're telling us to find part A, they're telling us to find. Okay, my pen is. So find V when dv over dt equals to 0. So we're going to make the whole differential equation, we're going to make it equal to 0. So negative v v squared minus 1 plus a v plus a, that's equal to 0. So this simply means that either negative v equals to 0 or the whole expression v squared minus 1 plus a v plus a equals to 0. If you have a product and you have two expressions that give you a product of 0, it means that one of them has to be equal to 0, or either both of them have to be equal to 0. So in this case, you divide both sides by negative 1, and we already have one solution for v. V equals to 0. In the second case, we can distribute the v and also distribute the minus. So we're distributing both the v and the minus, and that gives us negative v right there, minus av plus a. That gives us 0. And then we follow a process called factoring by grouping, where we group these two together and those two together. But remember, since there's a minus in between there, this plus is going to become a minus when we introduce that parenthesis. So then we have v squared minus v minus, in parentheses, minus av plus a equals to 0. We can factor out a v, which is the GCF in the first parenthesis, and we're left with v minus 1. And then we can also factor out an a, and we're left with another v minus 1. Remember, we said that that is going to be a minus, so we don't have a plus anymore because we introduced a parenthesis. So this becomes a minus. So this is equal to 0. In the next page, we're going to simplify this new expression. So we have v, and then v minus 1 minus a, v minus 1 equals to 0. This is common for both v and a, and therefore we can factor it out, we can pull it out and have v minus a, so combining this variable v and the variable a, and then putting the common factor there, that becomes equal to 0. This simply means that either v minus a equals to 0, and so if you add a on both sides, you get another solution, v equals to a, or v minus 1 equals to 0, so you add 1 on both sides, and so you get v equals to 1. Okay, so we have 3 solutions. In the previous page, you can see that the first solution was when v equals to 0. The second solution is when v equals to a, and then the third solution is when v equals to 1. And that completes the process for solving part A. In part B, the question is for what value is v increasing? When a function is increasing, it simply means that its derivative is obviously going to be greater than 0. That's what happens when a function is increasing. So dv over dt is greater than 0. And so you still go back and take the same inequality we had before, or rather the same expression we had before, and we have negative v, v squared minus 1 plus a, v plus a, 1 plus a in parentheses, that has to be greater than 0. We'll simplify the negative. We don't want to deal with the negative, so we divide both sides of the inequality by negative 1. So we end up with v. But remember from the previous step, this whole expression simplified to v minus 1 and v minus a, or v minus a and v minus 1. That has to be less than 0. The reason why it's less than 0 is when you divide by or multiply by a negative number, the inequality, if it's greater than, it becomes a less than. And these two have a relationship. You can see that v squared minus 1 plus av plus a simplified to v minus a, v minus 1. So at this point, we can use a number line to test for locations where the expression is less than 0. So we're going to do that on the next page. So we have a v minus a, v minus 1. If we check, initially it was greater than, and then it shifted to less than. So we have to take note of that. And then we're going to have an inequality and specific test points. So the initial test point, if you can recall, was a solution of 0. And then we had the second test, not test point, sorry, but these were the critical points, not the test point. These were the critical points. So this is A, and then we have another critical point, which is 1. I'm using holes because of this inequality. If we had less than or equal to, the character of the number line would change to solid points to reflect the equal sign. But since it's just a less than, same thing happens to greater than, you only have holes right there. And then I'm going to pick specific test points. This is -1. I'll pick 0.1, which is very close to 0. I'll pick 0.9, which is close to 1, just to make sure it's not close to A. And then I'll pick 1.1 to be on the safe side. So you plug in these numbers into the expression v minus A, v minus 1. So when you plug in -1, there's a certain outcome when you plug in -1 into the expression. So you can see this is a negative. -1 minus -A, regardless of what A is a positive number anyway because it lies between 0 and 1. It's going to give you a negative value. And then a negative right here in the last parenthesis, a negative and a negative will give you another negative value. So you're simply multiplying three negative values, and that means the initial part of the number line will all be negative. That's step 1. The second step, we'll take the 0.1 and plug it into the expression. So this is 0.1 minus 1, and then it's positive. A is obviously greater than 0.1 because A lies to the right of 0.1. So this part of the parentheses of this part of the expression is going to be 0. And then 0.1 minus 1 obviously has to be negative. So we have two negative numbers, and or rather two negative numbers will give you a positive. So this part will be positive. The next thing is to pick the 0.9. So we have 0.9, 0.9 minus A, and then 0.9 minus 1. So 0.9 is positive, 0.9 minus A, that means we have 0.9 is to the right of A. So it's going to be giving us a positive number in that parenthesis. 0.9 is to the left of 1, so it's going to be giving us a negative number. A positive times a negative, you can see that's going to give us a negative number. So in between A and 1, we have a negative number. And then the last test point is 1.1. So 1.1, 1.1 minus A, and then 1.1 minus 1. 1.1 is positive, 1.1 minus A obviously is positive because it's to the right of A, and 1.1 minus 1 is also going to be positive because it's to the right of 1. So anything that lies to the right of 1 will be positive. So now we have a number line, and we can use that to complete the solution and say that our inequality v minus A, v minus 1 is less than 0. This is true when the inequality, when the solutions lie to the left of 0, and also when the solutions lie between A and 1. So those are going to be our two solutions where the function happens to be increasing. So the function is increasing when a v is between negative infinity and 0, and the union of A and 1. So those are the two locations where it's increasing. In the last part of the problem, I'm just going to go to the next page. We're tasked to, they were asking us to find, this is part, not part B, but part C, because we already did part A and part B. So this happens to be part C. And in part C, we can see that we want to find where the function is decreasing, and that simply means that dv over dt is less than 0. We're going to write out the expression again. So negative v, v squared, this is a square bracket, make it easier, 1 plus a. I think we had a v outside of there, so we just have to go back and verify that we have the right expression. Yes, we have v outside, so v, and then plus a. That whole thing has to be less than 0, Again, we divide both sides by -1 so we can get rid of the negative on the left side of the inequality. So we end up with v squared minus 1 plus a, v plus a is greater than 0. If you can recall, when we simplified the expression v squared minus 1 plus a, v plus a, we ended up with v minus a, v minus 1 is greater than 0. And that means we're going to get a new number line, but it's no different from the previous number line since the test points are the same. So we have a test point here, and that test point happened to be 0. We have another test point, not test point, critical point, sorry. So we have a critical point there, which is 0. And then we have another critical point A and then another critical point 1. We're still going to test the same points, 0.1, and then we'll test another 0.9 and then 1.1. Going back to the previous slide, you can see that when we tested those four test points, as in -1, 0.1, 0.9, and 1.1, we were able to get negative solutions right there, positive solutions between 0 and a, negative solutions between a and 1, and then we also had positive solutions beyond 1. And so looking at our inequality, we want to find where the expression is greater than 0, and that happens between 0 and a, and also beyond 1. So our function is decreasing. Our function is decreasing when a v, or the solution, lies between 0 and a, and also when our solution lies beyond 1. So, those are the steps of finding the solutions. Just going back to clarify what happened. Initially, we had dv over dt being equal to 0. That means the neural, the electric impulse of the neuron, Vt, is a constant. And so we factored a couple of variables, distribution process. So we used distributive law in second page, and also we used GCF factorization, and that helped us to simplify the problem. You can recall that we had our first solution, which is v equals to 0, and then by the time we got to the third page, we had two more solutions, v equals to a and v equals to 1, and this is similar to what you do when you're solving quadratic equations. And then in part B, we had to find the function when it's increasing, and that means dv over dt is greater than 0. So we use that inequality. We still factor our problem. We divide both sides by -1 because we want to end up with a simplified expression. That just changes the inequality to a less than sign. We simplify. We use the critical values to build a number line. Remember, we have holes because we're dealing with inequalities. And then we put test points, -1, 0.1, 0.9, and 1.1. Simplify that, we find this solution, and we repeat the same process to find where the function is decreasing. I hope you enjoyed the whole process of solving the problem. Feel free to send any comments or questions or anything that you need to add on to the problem. But remember, increasing and decreasing functions are used a lot in applied problems in calculus. Thanks and bye, and have a great day.